Okay, after after leaving MIT, I went to Harvard. I went to Harvard thanks to a letter, a specific letter, a very warm recommendation that Francis Lowe wrote to my former colleague Stephen Weinberg at Harvard. I want to be on record. I want to read this letter on record, also with my appreciation, of course. Anyhow, I landed at Harvard. Harvard is a different place. People who have not been at Harvard, I don't know whether they understand what the word Harvard is. Harvard is a cathartic place of science in which it's like a volcano, but a volcano inside a star, in which things happen in a brilliant way, usually not seen outside. Is the ideal place for physicists who wants to test their capability and their strength and their will. For instance, if there is a physicist out there who wants to work out, let's say, as an example, a generalization of Einstein's general relativity for a better description of gravitation, the place to go is Harvard University. Because they will be faced with giants in science who will attack them and crush them like flies. So unless they have the guts, they have the capability, the determination, the deep knowledge and the resistance and the conviction of their idea, they will not survive in seconds. Also, Harvard, as well as MIT, Harvard is not a place where scientists can go for consultation with others. If you need consultation at Harvard University, you are not Harvard material. No, you sit and wait for others to come and consult with you, if it may happen at all. Usually young people may come, but certainly not colleagues, may come for consultation. But this cathartic place of contrast is the ideal scenario for discoveries. Indeed, everything essentially, the name hadronic mechanics was born at Harvard University. I proposed it in 1978. The mathematics of hadronic mechanics, the foundation, as you will see soon, was born at Harvard University. My Lie-Isotopic and Lie-admissible generalization of Heisenberg equation, which is the very essence of hadronic mechanics, were born there. The first application for the synthesis of meson from lighter leptons was born there, and many other developments were born there. So all in all, I have a great recollection of my stay at Harvard. I loved every moment of it. I loved the fights with my colleagues, in which I respected the review to a certain extent, because then I had my way of doing physics. Let me put it in a different way. The problem that I was addressing were too much important, in my opinion, for the advancement of new knowledge toward, remember my first word in lecture 1A, toward the conception and the industrial development of new, much needed, new, clean energy and fuel. This need by mankind, the need to study those problems, the need to surpass Einstein, quantum mechanics, and everything had to be surpassed to achieve this social goal was by far much more important than the objection by my distinguished colleague at Harvard University. So certainly they did not stop me. As a matter of fact, I am very grateful because their strong objection was enormously stimulating for me. It was exhilarating, if I can use this word. So in conclusion, I have nothing but an expression of deep appreciation to Harvard University for having me as a member for a number of years, under several contracts for the Department of Energy that are known. Thanks also to my colleague at the Department of Mathematics, Shlomo Sternberg, a person I respect dearly, both scientifically and personally. And also, finally, there is one comment I have to make. I am very grateful to my colleagues because they elected not to be part of my research. In so doing, they gave me a fantastic gift. They gave me the gift of scientific priority. They were giant. I was a little fly. So if they had put their names in my study, the scientific priority will be theirs. Now it's mine and mine alone. So I cannot but say thank you to my colleagues and thank you for the hospitality. Let's get going back to a review of what happened at Harvard, scientifically. Well, I landed at Harvard with the conviction that indeed there existed a consistent step-by-step generalization of Lie theory of isotopic type, namely of axiom preserving. So the axiom of Lie will remain, but the realization will be broader. Okay, but I arrived there only with the conviction this existed at the classical level. Of course, I needed an operator version, or a matrix version, if you want. So my first job was to identify the operator or matrix version, counterpart, if you want, of the Birkhofian brackets. Well, actually should not be Birkhofian, they are called now Santilli classical Lie-Isotopic brackets, but in any case I still call it Birkhoff because they derive from Birkhoff. So this was my job, and after trying many errors and a long series of long days and nights of trying, finally the simplest solution turned out to be the best. Namely, what I did, I lifted in an isotopic way the fundamental associative product of matrices by sandwiching in between a matrix T, today called the isotopic element, with the dimension of the base, or the dimension of the other matrices of the set, if you want. This lifting is isotopic because it's still associative, and I restricted the isotopic element to be positive definite to avoid all sorts of topological complication and so on. It was then very easy to build the corresponding bracket that today is called international. There are many books, 15 or 20 monographs on this, called Lie-Isotopic bracket, and which is derived from the isotopic associative law, and it was very easy to verify that indeed that the Lie axioms are verified. Indeed, they remain. So I became convinced of the existence of a step-by-step lifting of Lie algebra from quantum mechanics all the way to the most general possible operator algebra. It was at that moment that the fights at Harvard began. But they did not know that by that time I had discovered this possibility. This is an enormous possibility, lifting Lie theory in an axiom-preserving way. My God, the applications are endless, not only in science. Later, as I had suspected at that time, the industrial applications are numerous. And indeed, so therefore I had no interest whatsoever in an academic career at Harvard. No, this was too big and way surpassing any possible interest in an academic career. I was interested in knowledge, in new knowledge, and that's what I did pursue. And that's what I recommend to all my colleagues. Now, so once, in the meantime, when I was during my PhD studies in Torino, I had written a little book on Lie theory. So I know a little bit of Lie theory. I had been a member of lots of lectures on Lie theory. So it was very easy for me to lift each and every aspect, lift isotopically, namely in an axiom-preserving way, each and every branch of Lie theory, and see what the result was. Unfortunately, and I published this in 1978 in this memoir, unfortunately most of these results are presented in my style as a particular case of the much broader Lie admissible lifting of Lie theory, because I always work at the most general possible way, then I specialized. So it took some time to propagate to the physics, and sometime more time to propagate in the mathematical community. But the first thing which I did, I lifted the universal enveloping associative algebra, which is the foundation of Lie theory. This was very easy to do, to lift the Poincaré-Birkhoff theorem. It's called today Poincaré-Birkhoff-Santilli theorem, which is they're called with this ordered isomonomial is an infinite dimensional basis. This was very easy to do, no big deal. What I was interested in the meat, the substance. The infinite dimensional basis of the enveloping algebra characterized the exponentiation. The exponentiation is at the foundation of the Lie transformation theory. So I want to know whether the exponentiation remained conventional or was lifted. And this was in late 1977, early 1978. I immediately saw that the exponentiation based on this broader envelope was by far non-trivial. Why? Because the isotopic elements appears in the exponent of the new exponentiation, the very, very exponent term. This clearly means lifting the very simplistic, let me say so by today's standard, not by the 2 centuries ago, by today's standard, lift the simplistic structure of Lie theory into the most general possible, non-linear, non-local, integral differential form. Because of this, the functional dependence of this isotopic element is completely unrestricted. Provided it's positive definite, can depend on wave function, their derivative, can depend on the most complicated integral differential expression you can think of, and this thing remains. Once I saw this, then nobody will stop me. There was no way anybody could possibly stop me. Then I immediately lifted the various Lie theorem. Here I quote only the lifting of the Lie second theorem, with a novelty that still today is ignored by mathematicians to their peril. I'm sorry, others will do it. What is it? There was the clear emergence of structure function. Structure function. Lie theory only admits structure constant. It was inevitable. This, if you look at the structure, I don't have the time to explain, but by studying the literature, interested colleague can see it. This has an enormous implication for the representation theory. Let me give you a glimpse. First of all, it broadens the representation theory of Lie algebra in a dramatic way. Secondly, from a physical viewpoint, it's far non-trivial. If the structure here are constant, we only have structure constant, then the only admissible spin for an electron in the core of a star is 1/2. Namely, there is no mutation or lifting of spin. However, and this is unfortunately something I cannot accept, because how can possibly an electron inside a black hole or a quasar have the same spin as being when it is a member of the hydrogen atom? And sorry, I have to study the most general possible case, and then eventually, depending on evidence, go back to the 20th century conception. That's what my science the drive tells me to do. In this case, however, if we have here structure function, then the spin of an electron in the core of a star or inside the black hole is an arbitrary quantity. It becomes an integral differential expression depending on local quantity, as it should be, as in the most general possible formulation. At the moment, however, the electron exits the interior condition, immediately reacquires spin 1/2 and conventional with secondary effects. So I want to repeat, this feature has been ignored by mathematicians, with namely the alternative structure constant and function, as well as the related ISO representation, namely the representation of the Lie-Santilli algebra, has been ignored so far, to my knowledge, by mathematicians. I hope they will pay attention, because the physical implications are dramatic. After that, it was very easy to lift Lie transformation group by verifying that indeed the composition law is associative. There is indeed an inverse under this generalized isotopic associative product. And of course, the commutativity of the composition law. All the basic requirements of Lie transformation groups are preserved in a trivial way. You have to expect that, because you preserve the axiom. Since you preserve the axiom, you preserve all the main features. If you miss any of the feature, it's not an isotopy. No, by very conception of the isotopy, you have to preserve all characteristics of the original theory. So, and this was the end result of what is called today a Lie-Santilli isotransformation group, which is extremely non-linear, non-linear, non-local integral, non-Hamiltonian, etc., etc. It's the most general possible transformation group, verifying the Lie axiom. Verifying the Lie axiom that I know many, but many more general, very general, but they don't verify the Lie axioms. Okay, and then the last thing that I did in 1978 was the lift the Baker's-Hausbert theorem to verify indeed that it holds. It does hold. I was expecting, but the very notion of isotopy, just to make this is essential to verify the closure of the, as everybody knows a little bit of Lie theory, and therefore this was indeed verified. So this was essentially the main result for the Lie-isotopic theory that I achieved in 1978, well, between 78 and at Harvard, namely again the classical part I did at MIT, the operator or the matrix part, we are not talking about operator at this level, The matrix part was achieved in early 78. But that's all I did at Harvard, because at Harvard I worked at the covering level, which is of the irreversibility, which is my primary field of interest. This was kind of a side research. Subsequently, then I left Harvard, and then in subsequent years, we discovered this property, which is one of the most fundamental features of the Lie-Santilli isotheory. It's a theorem that allows you to construct, that if you know a Lie symmetry, allows you to construct very easily all infinitely possible Lie-isotopic symmetries. This is non-trivial, ladies and gentlemen, for the interior dynamical problem, as I hope to be able to show not today, but in future lectures. What does the theorem say? Suppose you have a metric or pseudometric space, and suppose with a certain symmetry. And as you know, this is the expression generally for the symmetry, for the invariance of the metric itself. Well, suppose now you change this metric by multiplying with an isotopic matrix M of the same dimension. So if this metric is Euclidean, this is 3 by 3. If this is Minkowski, this is 4 by 4, etc. And this T is positive definite. So you preserve the topology of the signature of the original metric, okay? So if you lift the metric in this way, then and use the isotopic element to build you use all infinitely possible isotopic element, you will be able to apply the Lie-Santilli theory as presented in preceding charts. There is no need for additional fancy. I'm making this statement for physicists. It's very easy to apply. Just you look at the iso exponentiation and do everything else as presented, and you automatically reach all infinitely possible generalization of the original metric and all infinitely possible symmetry of that generalized metric. It is automatic, it's guaranteed, you don't even have to verify it. Moreover, what really intrigued me was that all those infinitely possible symmetries so constructed, they are locally isomorphic to the original symmetry because of the positive definiteness of the isotopic element T. So, ladies and gentlemen, this is indeed, this was when I achieved this result, it was indeed an undescribable moment, because it was the thrill of the real thrill of discovery. Because this is essentially allowing me not only to have one result, but all possible results I was looking for symmetry and therefore quantitative treatment of interior dynamical problem. I remember this was in the middle of the night when after many days of very hard work, and my wife Carla thought that something had happened to me, because even the expression of the thrill of discovery is indescribable. Unless you live it, it's very difficult to describe. So basically, these elements gave us the foundation. 1978. You will hear very learned scholars presenting you this in a very proper, complete mathematical language, but the essence is there. If you look at Jupiter, the last theorem tells you that we can easily preserve the 10 total conservation laws, either Galilean or Poincaré, whatever you prefer. Why? Because the generator do not change in going from, by conception and construction, the generator do not change in going from a Lie to a Lie-Santilli isotheory. Why so? You have to do that. Otherwise, if you change the generator, you no longer can verify the 10 conservation laws. As you know, the 10 generators of Galilei symmetry are the conservation laws, so you cannot change them. So the generator are not changed, but the structure of the Lie symmetry is lifted in the most general possible, non-linear, non-local. So I do less, I preserve the physics of the conservation law, but I am no longer restricted to point particle in interior condition. So I can do some new physics as far as the structure is concerned. I can represent vortices with a locally varying angular momentum and other things that are beyond any dream of possibility by using 20th century science. But as it is the fate of all discoveries, there is then a moment of reflection. After achieving this result, I spent years of critical examination of the result. Otherwise, we know the discovery will not resist the test of time. And the end result, which is the conclusion of this first lecture, is be careful. Because if you use all the results of all the presentation which I made in a moment ago of the Lie-Isotopic theory without their elaboration with the novel isomathematics, which I didn't even define, will be lecture 2b. Unless you use isomathematics, the theory is catastrophically inconsistent. Catastrophically inconsistent. So I had to declare my own construction to be catastrophically inconsistent. I wrote a monograph published in one of the best publisher of the time, Springer Verlag, in their best series under the name Birkhoffian generalization of Hamiltonian mechanics when I was at MIT and Harvard. Later I had to declare for honestly that as presented, that monograph is catastrophically inconsistent under the time evolution. Of course, later I discovered what to do to resolve the inconsistency, but this will be the subject of the next lecture. Thank you for your attention.
Professor Santilli, non-Hamiltonian systems emit coordinate transformations allowing to recover Hamiltonian formulations. Why do you not use them?
Yeah, this is a very nice question. I really appreciate being asked. Indeed, in the two books published by Springer Verlag, you can find a number of versions of the so-called Lie-Koenig theorem and other theorems, according to which, under certain topological conditions, a non-Hamiltonian system in a local chart, in certain coordinates, can indeed be transformed into a form that is indeed Hamiltonian. And once you recover an Hamiltonian form, you can apply the totality of the 20th century mathematics. So the question is very pertinent. So why I don't do that? Well, we tried, of course. Myself, this was debated for years, to use this type of transformation. But the reason is that, first of all, under this transformation, I lose in any case all relativity and all mechanics. And why? Because those transformations are necessarily highly nonlinear, non-local, non-Hamiltonian. So you lose all possible inertial systems, so there is no way of even formulating Galilei and special relativity and quantum mechanics. So it's a kind of cheating, you know. You give the perception, oh, I have an Hamiltonian, so I apply 20th century mathematics and physics, but then you dig and you don't have it. But there is another reason why. As I indicated before, our intent is to do science, which means mathematical treatment producing numbers, and those numbers, most importantly, have to be subject to verification. To do experimental verification, you need equipment. So, if the equipment are heavy, if I have a certain detector is 2 or 3 tons, I cannot put this detector in an hyperbolic, nonlinear interdifferential trajectory just to recover Hamiltonian mechanics. I cannot do any real serious science. No, because of this, the entirety of all levels of investigation in our field, in hadronic mechanics, is one of the central requirements of the entire mathematical, physical, chemical formulation of hadronic mechanics is called a direct representation. Namely, all representation, whatever they are, must occur in the coordinate of the observer, and not in hypothetical nonlinear coordinate that gives you the impression of the dream of having preserved Einstein, when in reality, or quantum mechanics, when in reality you cannot. So it was impossible. It exists, yes, the transformation exists, but we could not extract any serious science out of it.
In 1982, you wrote a very nice monograph on the Birkhoffian mechanics published by the best scientific publisher of the time, Springer Verlag. But subsequently, you abandoned the Birkhoffian mechanics in favor of different mechanics. Could you please explain why?
Well, this is also an excellent question, and it's very pertinent indeed, because the Birkhoffian mechanics achieved direct universality, namely in the representation of all Newtonian interior dynamical system. So the representation capability of Birkhoffian mechanics was and remains impressive indeed. The problem is that, as we will see in the next lecture, and I cannot do it in this lecture, we will see that the structure is non-canonical, and therefore, as it showed several years later, showed a very serious limitation under the time evolution law, and forced the construction of a new mathematics. In other words, the Birkhoffian mechanics, as published in that monograph, is perfect as a Polaroid shot of reality, namely without time evolution. Then yes, everything is perfect. However, if you include the time evolution, you have to lift the base fields, you have to lift the functional analysis, differential calculus. You have to use new mathematics, specifically conceived for the structural generalization of Hamilton's equation. That was achieved later on. But later we discovered that Birkhoffian mechanics cannot have an operator counterpart that is manageable per our knowledge for technical reasons that we will see. So this caused an endless search of alternative formulation of Birkhoffian mechanics into forms that eventually will admit a map, a consistent, simple and consistent map into an operator form. Because our clear the decision was to start at the Newtonian level and then go to quantum mechanics. So unless we reach the classical representation was the fundamental, had to admit an operator counterpart. Birkhoffian mechanics does not. And that's the reason why I was forced to, even though I'm the author, I was forced to abandon for a series of sequential mechanics, all of which resulted to not to have this crucial clear image into the operator form for technical reasons that we will discuss in the next lecture.
Professor Santilli, I have doubt as to whether you really have to change the mathematics to treat deformations of Lie algebras. In fact, all Q deformations of Lie algebras are treated in the best journals via Lie mathematics. Please let me know your view on the issue.
This is another very nice question. I'm so glad that you asked. Thank you. Because it goes at the very, very heart of this catharsis of creation, or at least trying to create something, and then discover that it is indeed not insufficient. There are limitations. What are the limitations? How we can surpass it? That's why it took 50 years to do this job, by many, many physicists, not only mathematicians. The reason are essentially the same as the same insufficiency of Birkhoffian mechanics. Namely that, but the gist is essentially the following. This has happened repeatedly in history. Suppose you have a mathematics that works magnificently well for a given problem. Typically, for instance, Hilbert space for the structure of the hydrogen atom. It works magnificently. Then all of a sudden, you want to study the hydrogen atom compressed inside the sun synthesizing the neutron. So what you do, you change dramatically the physical condition. If you try to use the mathematics that works so well for the original condition, you will never reach results that will withstand the test of time. Because then if you change dramatically the condition of the structure that you are studying, you must change the mathematics accordingly in a way and achieve consistency. For the case of Lie, you see the reason why the presentation was as I presented, I presented the way it was derived to give a perspective of this evolution, also to justify the next step. Is precisely an illustration of the point. Here you have Lie theory, is majestic. The mathematics underlying Lie theory is majestic in functional analysis, topology, differential calculus. It's beautiful. But now you lift the theory into an extremely non-linear, non-local, and integral differential form. If you use the mathematics of Lie, which means functional, use cosinus and cosinus, the ordinary differential, the Zeeman topology of Minkowski space. This is all beautiful stuff of Lie theory. Ladies and gentlemen, you are heading for catastrophic inconsistencies that I will identify in next. You lift theory, Lie theory. You have to lift the totality of the mathematics in a consistent way. Then you have a truly results that will indeed, and has, I believe, we have achieved a result that indeed has already withstand the most powerful criticism so far with no scratch whatsoever, and I believe it's something worth working on and fighting for.